What's that?
No, I'm not interested in listening words on. But this one will be only sets in the ecosystem.
So how are you?
No.
Okay. So today, we start with already late. So today we're continuing what we started last time, which is the challenges of tiny machine learning, right? Remember what we have done last time is we looked into the embedded system side, right? In the very first lecture, we defined TinyML as the intersection of embedded as a hardware and tiny or a system and machine learning, right? As technology. And then we said embedded systems, in fact, software and hardware. So what we have done last time is we delved into those challenges from the embedded system side, started by the hardware, and then went into the software, right? And that's what we stopped at last time. Today, we're going to move to the other part, the other set of the tiny machine learning, which is machine learning itself, right, as a pipeline, and try to understand some of the challenges that you will face in tiny machine learning that originally did not exist in traditional machine learning, right? And those are things that if you are aware of machine learning, you have taken a course in machine learning, usually you don't discuss these things, right? Because they are not really challenges for machine learning on its own. These are challenges for TinyML from the ML side, right? It's very important to understand this. And then hopefully towards the end of the lecture, we'll take like half an hour to talk about the survey paper, the project, and all of the things, like logistical stuff, to make sure we're all on the same page. Okay, good. So now, the first thing that you will face when you look into machine learning is that if you look historically into things, remember in lecture one, I told you like I love the history of sciences. Like if you understand how things evolve in the domain you are interested in, you'll understand the challenges and how things happen in the future, right? So for machine learning, if you look into, well, I think 60s is where people started looking into this concept of artificial intelligence, right? And then it faded down. And then in 80s, again, we had Jeff Hinton and some others trying to revive this using the concept of neurons and that stuff. But then they didn't have enough funding by then. No one believed that this is something that is worth really putting money on, right? And then it died for a few years. And then up until 2012, where we had AlexNet and some of these proofs that you inserted GPUs into the pipeline, and all of a sudden you have the compute you need, right? And then machine learning boomed since then. So if you look at what happened from 60s pretty much up until 2010 or around like the early 2000s, you will find that the growth of the size of the machine learning models, and we will see right now what I mean by a size of machine learning model, is very much linear, right? Things are not really increasing as much, right? This graph will not look like this, right? It's not exponential, right? If we just really open things from here, you'll start seeing, well, it's almost steady state or growing very linearly with a very slow rate, right? And the reason is, first of all, not enough innovation investments are being put in, not enough money, and also not enough compute resources, right? But then since 2012, when we had AlexNet and some of the very early neural networks that have shown using GPUs a great accuracy into trying to really learn back then, the very traditional data sets, NIST and some others, you will realize, well, we start putting in a lot of money, there's a lot of hope there, and the size of the model increases exponentially, as you see, right? Now, a disclaimer here is that this is even by the language of now is quite old, right? If we have grown that this is only ChatGPT 3, right? GPT-3. If you look into the recent models, this looks like here, right? Because the growth is even more than this, right? But I need really to update that graph because I'm reusing the same slide again from Rahul, which is quite old, right? Well, quite old with the language of today. It's less than 2 years old. Good. So why this is challenging for us? Because remember, we want things to be tiny, right? So we want things to be tiny. And that exponential growth of the size of the model is taking us completely away from this tiny concept, right? Again, to be able to run this few billion parameters or multi-billion parameters, you need a very, very powerful machine, right? You need a cloud compute, basically, right? OpenAI are basically burning billions of dollars daily because of this server stuff, right? Like just a single, I forgot the exact stat that a single interaction of you, for example, asking ChatGPT how to do something, I don't know, like go to some place or try to hack a certain system, or do like a very silly question, it's in fact causing dollars, right? And what scale this for the millions of users every day. If you look into, again, that scale, the computing needs grow by more than 300,000x to train those machine learning models because of the parameter size. And well, there is someone who's trying to come up with I would say a law. It's not a computer, it's an observation. It's similar to Moore's law, right? So in Moore's law, we know that the number of transistors double every couple of years, right? And this has been scaling quite well over the past 50 years, right? So someone tried to look into, well, what are we really having in the machine learning? Can we make an observation from the past history we had, right? Put aside that, in fact, this observation is very limited because every couple of months we see that the scaling is in fact way higher, right? But at least if it gives you some perspective, you see that the compute requirements double not every 2 years, which is the scale of Moore's law, assuming Moore's law is still really applicable. It really doubles every 3 to 4 months, right? Which means every 3 months, I would need double the compute capability that we have in the market. This tells you why NVIDIA is in fact booming, right? Like in terms of as a stock, because there's a lot of demand on the compute, and this demand is not even there, right? Like no matter what you really try to propose, you need a new one every couple of months, right? You need double of that, right? So from, well, again, it's a basic economic law. There's a supply, there's a demand, right? The demand is always preceding the supply with an order of magnitude. So you would always have people to buy that stuff from you and pre-orders, right? You hear about pre-orders from NVIDIA. So this Putin, and again, this is like in the early 2010s and after, big companies realize this fact. They realize that the compute unit is going to be the bottleneck. So we need to do something, right? And this something started in the machine learning aspect as a GPU model, right? Like GPUs were the solution, right? Because Andrew Ng from Stanford did that experiment. It worked very well, and then NVIDIA again boomed, and everyone went into GPUs. But then some other companies did a different approach. Google, for example, they came up with this TPU, right? Which is tensor processing units. These are specialized processing units, not general purpose GPUs, but mainly to accelerate tensors, which is the main kernel of a neural network, right? So they are specialized, well, they are processors, but in reality, they are closer to ASIC than a processor. They can be programmed, but only programmed for a very special functionality, right? And then I still remember because they published this first time in ESCA, which is the top computer architecture conference. I was in this presentation. The paper they have, I think, I don't know, 300 authors. They have very big number of authors in that paper. But this was only when they proposing really the TPU as, well, a single device, right? But 2 years later, they announced that in fact they had TPUs as servers, as racks in their servers working over the past 3 years. What does this really mean? It means that, well, Google has been using TPU pretty much that everyone's using GPU for accelerating server-based XCs, right? And then they had TPU v2 and like different versions of TPU. So this direction of having specialized processing units to accelerate only machine learning is addressing the need that we need double the compute. CPUs were following the track already. No one is using CPUs there, right? And this is a problem for time machine learning as we'll come into it, right? But the main trend is GPUs, and then Google took that side of TPUs. Are you aware of any other paradigm in accelerating machine learning? Other companies that are using something else?
Quantum.
Yeah, quantum for sure is another kind of visionary type of approach. But I'm talking about, yeah, you mentioned Grok, right? Which is using.
I'm not sure, but I know they have something.
Okay, yeah. There is Grok and there is TensorTorrent, right? So these are two big companies that are trying also to come up with their own ASIC chips that are specialized for AI acceleration. Grok is mainly focusing on, well, we are having the biggest wafer specialized with thousands of mini processors, mini cores, mini CPUs. So in fact, Grok is a CPU company But those CPUs are specialized. They are very basic pipeline, like a 5-stage pipeline, very, very simple CPU. But because we have thousands of them on one chip, we simplify the interconnect and we can accelerate machine learning. So that's one direction, which is reviving CPUs. Then another direction, which is tensor torrent. They also use RISC-V CPUs, but they focus mainly on inference, right? And inference is something that NVIDIA overlooked a little bit. NVIDIA or GPUs in general, because they're very power hungry, they're very big. They have been focusing on that training market, right? This is where the money is being burned. But they ignored the inference a little bit up until lately. I think they had a deal with tensor torrent 1 month ago, 2 months ago, where they almost bought it, right? To go to the inference market as well. Right? So the summary is, well, we need compute, right? And those compute has to go to servers, has to go to racks, have to be very big, and well, we have to start worrying about right now in the real estate market. If you ask the people in the real estate, what is the hottest kind of real estate deals you do, they will not tell you that you are buying big lands or are buying apartments near like downtown cities. They are buying lands for, you know what, for what? For data center, right? That's really the biggest thing in real estate, right? Why that's the case? Because again, we need those things to be very big. We need to be racked, right? We need to cool them. And that means they need to be put in a very specialized place, right? Those specialized places means you have access to the power, right? To the electricity mainly, right? This can come from, and also cooling, which is a very important thing, right? So the cooling can come from water, so they have to be near sea, or you can put them in like near kind of breathing temperatures. So they go, for example, for Denmark, Norway, and Canada to the north and try to build data centers there, right? I think Microsoft has data centers in Alaska, for example, right? So you need to worry too much about cooling as well as providing the energy source, right? Which is a business on its own. I think the Gulf here also is trying to really, because of the cheap oil, they try to enter the market offering electricity cheap, tax based for these big companies, right? If you read some of the business trends, right, in the region, you'll see that's also, this is a big topic at the moment. Right? But the point is, well, this is completely the opposite direction of what we do in that course, right? We're going to big up to the way of real estate. We want to be very, very tiny up to like a coin-sized microcontroller that we discussed in the first lecture, right? So what do we do, right? So going that big is important. It's needed for some applications, but our argument is, well, you need to stop, and you also need to think of the real life, daily life, kind of where the data really lives. This is the term that people use, where the data lives and being created. You need the compute there as well, right? So that's what we need here. Now, if we take that view and we try to look into some of those networks over the years and try to see the size and whether they are going to the big direction or to the small direction to understand the challenge, you can start again. Before AlexNet, again, things were linear more or less and not very interesting for everyone. But in 2012, you look into AlexNet and you see that we got around 50% accuracy, something that's very bad for sure. But your model size is 60 megabytes, right? Well, then sometime later on, in 2014, we had VGGNet. We achieved way better accuracy, right? So the trend is moving towards better accuracy, but at the expense of almost an order of magnitude higher memory size, model size, right? 500 megabytes, right? Compared to 60. Is that something in our direction? Well, the answer is no, right? Again, we're improving accuracy, but at the expense of memory, right? And then later on, well, we're just coming back to the model size, and we're able to achieve higher accuracy, but with a way smaller model size, 22 megabytes compared to 500 something, right? So we're moving back to the direction of small size of your network. And then, well, a very big step from Google, targeting mainly the mobile phones, right? To add intelligence to mobile phones. MobileNet version 1 and then version 2. Version 1 was not very good in terms of accuracy, but V2 was fixing this. And we're around 70% accuracy, but 60 megabytes in terms of size, right? So we're reducing way further. Now, the problem is that even with all this scale that we're talking about, And maybe this is one differentiation between edge AI as a term, right? Or mobile compute, so another course in mobile computing, and tiny machine learning. All of this, despite being quite in the direction we're looking at, we're still talking about megabytes of model size, right? Can we really run a megabyte model size into our tiny Arduino or ESP32 or that stuff? The answer is no, right? We cannot really afford this. We have to do something, right? So it's quite challenging there. We're talking about that in our board, we have a 256 kilobyte of RAM, right? We cannot even run like mobile net version. So what do we do, right? Okay, so that's the biggest challenge we have, is that all the model sizes, all the developments in the CNNs or like deep neural networks in general, even if they try to really reduce the size, they are reducing it at the scale of mobile compute and edge compute. They are not worrying too much about the tiny machine learning, right? So there is something that needs to be done. There is a big challenge to need to move from there up to here, which is kilobytes of memory, right? Now, how do we do this, right? Some techniques that we need to do. One of them is called pruning. What is pruning? Well, we look into the model size or the network itself, and we start saying, well, we have nodes and we have edges between these nodes, right? So that's really what constitutes your model. This is where these megabytes come from. So your two approaches to say, well, I look into the nodes, I try to reduce the number, or I look into the edges, I try to reduce the number, right? There is nothing else. And both are basically pruning, right? Pruning the edges basically means, well, being less dense, right? So you remove some of the relationships between the networks. And in that case, the model size, because you need to include these relationships, become less. Or you basically prune the neurons themselves, the edges, the vertices, right? The nodes. And in that case, you remove some of your nodes and your model size becomes less. Now, if it is that easy, what is the problem then? I would just look into a network, remove some of the nodes, remove some of the edges, and then I'm done.
You can destroy the accuracy.
Yeah, exactly. Like, there is always the tension about accuracy, right? I need to do all of this carefully while maintaining an acceptable accuracy, right? So if it was one direction, I have no problem. I can always give you a single neuron CNN, right? And I'm done, right? I can fit in anything. But what do you do, right? You're not looking really to do a healthcare personalized system and achieving an accuracy of 10%, right? 50% or whatever it is. So you care a lot about accuracy. This is why you're doing this pruning carefully while maintaining the accuracy of the system. This is where really the actual intelligence, the actual intellect come into play. Good. Now, pruning is not the only thing. I also go back to this network and say, well, yes, I removed some of the nodes or some of the edges, but I cannot really remove all of them. And well, assume to maintain certain accuracy and some architecture for the network, I ended up with this. Am I done? Is the only thing I can do? And the answer is no. You see in your real system, in a machine learning, classical machine learning system, and you see how you represent these nodes and these relationships, you find that you represent them as floating point numbers, for example, right? 64-bit floating point numbers. So, well, this is too much for me. This is maybe taking a lot of memory right now. Every single weight, for example, of that neuron is going to take 64-bit. Now, if I want to scale this down to a microcontroller, what do? Quantize it. This is where quantization comes into it, right? I look into the 64 bits and simply reduce this to 32, 16, 8 bits, 4 bits, 1 bits, binary neural networks, and this kind of discussion, right? So the more you quantize, the more you reduce the model size. But what do you lose again? Accuracy, right? So there is always also the tension between quantization and accuracy. So where do you stop? Well, it depends on what accuracy you're looking for. So you have to go through this iterative process of quantization and looking back to accuracy, right? So that's the quantization part. So what is quantization? Well, quantization is in fact a concept that we are borrowing from communication systems. Right? This is a very well-known, very old concept of communication systems. And it was used in communication systems because you wanted to reduce the bandwidth of transferring something, right? So quantization simply is you have a scale that you send numbers on, right? For example, for a channel, and you want to reduce that scale, right? In other words, a quantization is a way to do a many-to-one mapping, right? That's really what it is, right? Because you have a bigger scale and you want to a small scale. Right? So here, for example, if you have a float 32, then you have the minimum that you can represent with the float 32 and the maximum you can represent with float 32. Then I want to quantize this to int 8. In int 8, I only have 8 bits, right? So if this is signed, I can go from negative 128 to plus 127, which is simply negative 2 to the power 7, right? And then positive to the power 7. Okay? Now, if you do that quantization, you end up with those things, like the max here is going to the max here, the min is going to the min here, and all these numbers become closer, right? And some of them might be mapped to the same place. This is how you lose accuracy in quantization. Because someone can ask, well, why quantization is impacting the accuracy, right? It is because, in fact, the mapping, well, for example, these two values might be different, but eventually they are mapped to one place. Or the difference between them was allowing the network later on to differentiate between them. But right now, the difference is very minimal to the level that once they go to the other layers, well, it diminishes, right? Because again, like the bigger the difference between things, you as a human, you can classify them easily, right? But if they are very close, classifying them becomes very hard, right? So quantization, because it reduces simply your scope as a network, it impacts accuracy. Good? Questions? We'll revisit quantization and pruning in a lot more detail later on, but that's basically giving you the challenge of going from this big model size to the small one and how we address that, right? Questions? Great. Then there is this fancy new way of looking into, well, assume people have tried to really exhaustively explore pruning and quantization for a long time. Again, TensorFlow really gives you this, right? But then it might still not be enough, right? I told you earlier that in some of our healthcare research, we took the most famous 5 neural networks, and then we used TensorFlow and other frameworks, and we looked into whether they can fit into 4 or 5 different, like the most commonly used microcontrollers, like Arduino, ESP32, Raspberry Pi Zero, some other stuff, right? BeagleBoard, etc. And then we found that, well, you do your best quantization, your best pruning in TensorFlow, for example, TensorFlow. Then some of the networks still don't fit into some of the devices, right? Which I think is expected. So those networks are very beefy, they are very big, right? Then what do? Are we done? I mean, pruning quantization to our best and we still cannot fit. Is there something else we can do? And here comes this knowledge distillation part, right? Knowledge distillation is saying, well, there might be a more clever way of only looking into math, right? Because if you think about it, quantization is just a math concept, right? Because it's a mapping concept. And pruning is, in fact, an architecture concept because you just reduce things, right? But it's a more of an automated way. Now, can we do a clever way? This clever way is saying, well, think, for example, about an instructor that is working in an area for a very long time and want to explain a concept to a student, right? This explanation cannot really cover all the things that the instructor knows with a bit of a detail to the low-level detail. Why? Because, in fact, the student will get confused, right? Learning should be incremental as humans. So you try to abstract the concepts as much as you can, and you keep incrementally building that knowledge, right? This is, in the education systems, called knowledge distillation. Knowledge distillation is your ability to abstract a complex concept such that you can explain it, for example, to a five-year-old kid, right? Now, can we use that concept to really reduce the knowledge that is embedded in the model such that we build a simpler model that still holds the essence, the main idea of the main model? That's what people mean by knowledge distillation. How can we achieve this? For example, what you can do, or something we have tried on this paper that I'm talking about, we have taken the networks and tried to look into, if you manipulate their architecture, what really matters for the knowledge or the accuracy achievement that you're looking for in the healthcare, right? If we, for example, replace some mathematical operation with another mathematical operation, or if we simply say, well, this layer is not really adding much to the accuracy. So you start making big decisions about the architecture of the network itself, such that you create a simplified version of the network, right? This is knowledge distillation. Now, this is not an automated flow concept like quantization, for example, or pruning. This is something you make in a way that you are aware of the application you want to achieve, you are aware of the accuracy, and you are aware of the things that impacts the accuracy in the network. So it's like you open the black box of the network and you start understanding how it behaves. And based on this behavior, some of it is not very necessary for the accuracy, and some of it is necessary. You remove what is not necessary, you keep what is only necessary, right? So that's that concept. And in reality, most of the current state-of-the-art innovations are here, because this is already automated right now. Again, TensorFlow Lite and ECNN from ARM, like many things give you this, right? Because it's an automated process. This one's still not very much operated, right? There are a couple of papers that try to automate this as well, but this remains application dependent. Because what is important for an application is different than what is important for another application. So you cannot really automate it without understanding the semantics of the application. Good. Questions? So yeah, please. Yeah, automation means I feed a network to a tool, and then a model, and then I take another model as an output that is a reduced size. Right now in TensorFlow Lite, and we will see this, I think maybe not today, the next time, but we had the architecture also in the introduction lecture. You start by TensorFlow as a normal training model. You end up with a Python model that is a very big CNN model, for example. Then you feed it to TensorFlow Lite. It gives you a reduced, quantized, pruned, and optimized model size in C that you can deploy directly to the memory controller, right? So this is what I mean by automation. There is already an established flow that you give it an input model, big, beefy, cannot fit into the MCU, and it gives you a small, reduced size, optimized model that can fit, right? So here, pruning and quantization, again, these automated tools give you that. Up until now, noise distillation, not much. This is why a lot of papers are being published here. Other questions? Now, if you understand these three in the high level, all what we do in the rest of the course is in fact going through all these three, right? How do we achieve them, right? How do we really prune intelligently, how we quantize intelligently, how we use the tool to do this in different types of applications, and then how we do knowledge distillation, hopefully towards the end of the course. Good. Really explain that part to you. Yeah, so this is basically reducing the size of the network while maintaining its capability. Put in mind that the key constraint here is you want this small network to hold the essence of information of that big network, right? It's not a completely different network, and they should be doing exactly the same functionality. For example, in the healthcare, you should be achieving the accuracy or a close accuracy of this network using that network, right? Yeah, that's an excellent question. So if you go back to pruning, what you do is you remove either nodes or links, right? In that graphical representation. Knowledge distillation is not necessarily keeping that structure. For example, you can say, well, right now, I see that this layer is doing a max pool operation. Maybe max pool is a very expensive operation that is requiring a lot of compute. I cannot really fit into this microcontroller. I'm going to replace it with something simple. So you go into what really the CNN is doing. That's one thing, right? So you can change the type of the operation being done at one layer, which is, again, pruning has nothing to do with this, right? But also another thing that knowledge distillation is doing, you can think of knowledge distillation as the superset of pruning, because knowledge distillation is also simplifying the network, but not through only removing nodes or edges. It's through re-architecting the network itself, removing some of the layers, changing the operations of other layers. So it's more flexible in that sense, right? And this is why it's not very easily, up until now, automatable process. Other questions? Yeah. Okay, so what we are looking for, again, is, well, again, as I told you, the rest of the course is we're going to follow the normal machine learning pipeline, then use something like TensorFlow Lite. It will give us, again, the optimization, the encoding to see the quantization, the pruning as much as we can. And then the knowledge distillation will try our best to do on our own, optimize manually. And then you want to fit into this small device, right? That's your goal. This is what we call your normal TinyML pipeline, right? That's really how things are a little bit different than normal ML. So in terms of, again, those challenges, why are we doing this? You are doing this because, again, you are moving from something like this, which is, again, server-based, specialized, either GPUs, TPUs, or something else on a server, and you are going towards, first, mobile compute, right? Which is, again, I hear from you that you have done this already in Dr. Tamer's course, that you try to do TensorFlow Lite on the mobile phone, right? So it's one step closer, right? In your mobile phone, unlike a TPU or a GPU, you have way less memory, you have way less compute, or, well, you can also replace a mobile phone with a Raspberry Pi, for example, right? It's the same level of complexity. And the key idea here is you're not interested in doing training on your mobile phone, right? Because this is a big difference of TinyML compared to classical machine learning paradigm. This is why both are in fact separate worlds, right? When you are doing training, you can assume you have the most powerful compute in the world you have. But the key idea about TinyML is running inference should be real, should be impacting our daily life. I cannot really be running the inference in some cases while I'm in the server. Because again, the latency, I told you at the beginning, well, you are driving a car and then you are detecting some sort of a camera feed. And this camera feed comes to you, need to send it to the cloud, do the inference, send you the decision, and then you stop the car, right? This is not acceptable in real-time behavior. So you have to do the inference in these micro devices or small devices, extremely resource-constrained devices in real time where the data is being collected. Right? I think going from the mobile phone, this is, again, edge AI, mobile compute stage, right, or paradigm. But then for us, we are more into this tiny, small device that will even have more resource constraints, way less memory, way less compute, and power consumption requirements, right? So for TensorFlow Lite, if you want really to compare what is TensorFlow versus what is TensorFlow Lite, having this discussion in mind, you can say that a TensorFlow Lite is mainly used for the training pipeline, right, in TinyML. And this is also usually done by an ML researcher trying to optimize, for example, the network architecture itself. You come up with a new CNN, for example, right? So you're experimenting, you're changing things, you train and see the accuracy. So you are working on that side of things, right? You're an ML researcher. While for TensorFlow Lite is not really intended towards coming up with a new ML, right? Or a new CNN, or optimizing the training process. No. What is really concerned about is that you already have an inference model that is big enough. It's not really fitting you. But then you want to fit into a tiny device, then it goes through TensorFlow Lite to give you the application that is optimized, right? So it's more to an application or a developer targeting edge devices. Now, distributed or cloud-based infrastructure, do we need it for TensorFlow? TensorFlow here is an analogy of training, right? Well, definitely you need it, right? If you want really to have a good model. What about TensorFlow Lite? Not at all, right? The actual goal is to run into a microcontroller at the edge, right? So no cloud compute, no distributed infrastructure. Now, what about the binary size or the model size? In TensorFlow, do you really care? The answer clearly is no, right? I'm assuming I have the most powerful compute in the world. In TensorFlow Lite, that's your number one goal, right? We have TensorFlow Lite because of this, right? Because of reducing the model size. Now, in terms of weights while you're doing training, this is something that is really varying, right? Like you optimize your weights, you change them, you keep changing them during the training. While your weights for the TensorFlow Lite are, in fact, if you open, we'll see into this later on, like if you open a TensorFlow Lite model file, you will find that the weights are defined as, for example, constant and 8 in an array that is fixed values, right? You don't change them because we are doing inference at the moment, right? They're very quantized, so this is fixed and minimized as well. And what about topology? Well, the process of training and machine learning, for those that don't know machine learning, when I say we're doing training, what you really do, you try to come up with the model that you're going to deploy, right? What is this model? This model is really the architecture of this network, right? So if you go back here, something like this, right? What training is doing is, in fact, trying to figure out how do I assign the weights and the topology of these nodes, right? To get the best accuracy I'm looking for. Now, while you're doing inference, you already came up with a model. So the model is fixed, it doesn't change. The topology doesn't change, the weights don't change because you already trained the model and you came up with these weights and this topology, right? So it's here is fixed, here is value, right? Why this comparison is important? This comparison is important because it tells you how we really materialize the differences between TinyML and ML, right? In ML, most of the effort being done by researchers is here, right? While in TinyML, I care the most about the inference, right? Recently, well, past year 2024 and onwards, people started really publishing papers on onboard training, right? Can you do retraining on the MCUs? My personal perspective on this is like this is a fancy research paper to publish, but might not really be need. Why do I want to do this? Unless you are trying to do reinforcement learning because you want this also to be runtime. There is no other reason why you really want to train on your minimal device board, right? Because you want your model to be as accurate as possible. So you want to use the powerful compute to do the training, to come up with the model that is good enough, then focus your efforts to optimize that model to put in the microcontroller, right? So the real practical way of doing things is you assume training has all the powerful things that you, like all the powerful compute, the server machine, that stuff. You come up with a good model, and then you deploy this into your microcontroller because there you want the power consumption, you want the low latency, you want the low power, like the minimal compute and memory, all that stuff, right? So the flow looks like, well, I train using TensorFlow. I'm done. At this stage, I end up with a model. This is a TensorFlow model, right? This model is in Python mainly. I feed it as an input to TensorFlow Lite. It gives me a C model. This C model is in the format of .tfl Lite, right? As we will see. And this is quantized, pruned, and optimized. Then finally, I deploy in whatever device I'm looking for, right? In mobile compute, in the mobile course, you have done all of this and you took it to your mobile phone, iOS or Android, right? In our case, we even want to do this in a smaller size thing, like in our tiny device, right? Which is even, as I said, less memory, less compute, and focus only on inference still. Good. Okay, so revisiting this pipeline that we have seen in lecture 1, I'm training my model in TensorFlow. And then once I end up with a model, everything afterwards is my TensorFlow Lite, right? Converting the model, optimizing it, pruning it, and then you deploy it. Deploy it means, well, you are able really to load it to a microcontroller, and then finally you make the inference in real time to the edge. Good. In your project, you are expected to go through this pipeline, right? You're expected to build your model, come up with the inference model, you optimize it using TensorFlow Lite, right? Quantize and prune, all that stuff, and then you deploy it in the device live, having the sensors connected, and then we see it in the demo running in front of us. Okay. Questions? Good. So yeah, this deployment then, as we said, it can be in mobile compute or edge devices, Raspberry Pi, again, iOS, Android, whatever it is, or it can be on our tiny devices using an ARM Cortex M4, right? And then finally, you want the inference to be run at the edge. The edge can be a mobile phone or can be our microcontroller. Right? Questions? So just to summarize what we have done, looking into those challenges of machine learning, it tells us why you are having the pipeline you are having at the moment, right? We have a problem with the model size. We have a problem from the hardware perspective that we discussed last time, right? And from the machine learning side that we discussed today, which is mainly about model size and distinction between accuracy and model, right? Usually, the bigger the size, the higher the accuracy. And we want to challenge this by saying we want to reduce the size while keeping the accuracy as much as we can. How do you reduce the size? Pruning, quantization, with distillation, right? What helps us with this is the pipeline itself. Again, TensorFlow and then TensorFlow Lite is an example of that flow. So you start by training, you end up with a model. This model is a TensorFlow. You convert it using TensorFlow Lite. You end up with a TensorFlow Lite format, and then simply you deploy. We will see when we open a TensorFlow Lite that again, it's mainly constant arrays, right? That's really a very simple C file with all the weights there. And then you simply deploy it in your microcontroller. And finally, you have a real-time data, again, sensors, like whether it's like sound or images. It's like in our device, we have a camera and we have like a microphone, and then you use the model that you are running in the microcontroller to make your inference. Good. Questions? Okay, good. So let's have a 2-minute break. I'll just flash the other slides, and then we can continue, okay? But only 2 minutes because, again, we're already starting too late and we want to finish early. Yeah.
For the survey, we already submitted our group.
I will talk about this towards the end of the.
Yeah, but we want to add another member. We already have 5 and we want another one. So if
Yeah.
I create a new submission,
Can you edit the other one or once you,
I am
oh, because
not
it's a form you cannot. Okay, that's fine. Create another one. Yeah.
Okay. Because I told you earlier that I don't love working for 3 hours and I don't think it's the best way to learn, right? So an exercise of what we have done so far, which is understanding those challenges, machine learning, both at the model size perspective, which is the ML perspective, as well as the hardware perspective, which is the embedded one, right? This is the paper I was discussing with you earlier in the healthcare domain. It's done by my postdoc a few years ago. But the key idea is in this section, proposed methodology, you will see that we go through a machine learning pipeline. Yeah, I will come. You will have to open the paper in a second anyway, right? So basically, what we have done is we went through the normal pipeline. Up there, you will see a figure. Yeah, I think this one. You will see a figure that is talking about the training part as well as the inference part, going through all the stages, right? Data collection from sensors all the way down to actual really doing the inference and the decision, right? And you will see that what this paper was doing is in fact was taking vital signals, mainly ECG and BBG data, and trying to infer the blood pressure, a very common problem in personalized healthcare, right? To avoid the cuff-based blood pressure. But that's not really very important for this, right? That's the actual application is not very important. What is important is in this section, which is the methodology section, we have been discussing starting from here. For every single stage of the pipeline, the classical machining pipeline, we reflect on what needs to be revisited if you are doing this for time machine learning, right? And this was one of the early papers that have done this, right? So what you need to do is the following. Put in mind what we have studied last lecture, level 10 now, this first half of the lecture. Go through that section, it's like only 2 pages and a column, I think, right? You spend 10 minutes going skimming through it. You don't have to read a word by word. But we want to open a discussion after that 10 minutes, maybe for another 10 minutes, of what are some of these considerations that were discussed in that paper in every stage, right? We'll take them stage by stage and see, okay, for this stage, what do we need to do, right? Just to give you an example, we'll see that even at the data collection side of things, right? What features do you extract? Because put in mind, when you do your project, you are collecting real data from sensors, right? This data, for example, can be an image. It can be a vital signal like here, ECG or BBG. But then the first stage is to do what we call feature extraction, right? This is how the model is being based on, because you cannot really feed the whole thing to the CNN, the size will be huge. So you need to extract features. You need to define your features. Now, when it comes to an MCU, well, classical machine learning first, they try to maximize the number of features as much as they can. The more features you extract, the better it is. Well, this is a trend, right? It's very well known. Why that's the case? Because again, the more features I extract, the more I know about the input, then I can do a better model. Is that true for MCUs, for TinyML? Well, not necessarily. And this is what the paper is discussing at this stage, because if you collect more features, first of all, the math to extract these features from the signal is going to be huge. Because some features, in fact, would require a log operation. Some will require a max operation or a nonlinear operation or a floating point operation, which are very costly for an MCU. So even selecting your features to extract in the full pipeline is something that you have to reconsider in TinyML, right? That's one example in the first layer. Then we continue with the rest of the layers, right? So take 10 minutes, go through it, and then we'll open a discussion to hear from you what you understood for every single stage. Okay, this is already on iLearn. I added as like for today's lecture, lecture 2, I think. You'll find the paper PDF on iLearn. Good. Yeah, I see everyone is focused. Do you need more time? You guys are good? Okay, so what did you get? Let's start by the first stage, the pre-processing stage.
So some medical grade sensors were used to reduce the load of pre-processing like the code.
Yeah, that's in this example, right? But generally, what you need to consider. In the yeah.
Pre-processing depends on the inputs and the application itself. So
Yeah.
application you want to do. Okay.
Yeah, that's an excellent point. The pre-processing requires on that, depends on the application, how much accuracy you need. It also depends on how sensitive is the input data to noise, for example, right? Because some data might be more resilient and hence you don't need a lot of pre-processing. But what else?
I think you need to consider also exactly what data you need to pre-process for the on the device itself.
Yeah.
Because a lot of it would be noise, also you can disregard.
Yeah.
There was a part mentioned on synchronizing data, so in
Yeah.
addition to cleaning it.
An excellent point. If you are having a complex where data is coming from different sources that needs to be synchronized, this has to be taken into account. Now, again, are these things that we don't consider really in the traditional ML pipeline? You do, but not with the same importance. Because, for example, this synchronization thing, when you consider the traditional ML pipeline, you usually say, I can do the math to synchronize them, right? So this is why the pre-processing stage in ML pipelines, you can invest a lot of math and compute into it without worrying too much, right? Where is the problem? The problem is you are not only doing the pre-processing at the training phase. Pre-processing will be needed when you do inference because you are taking live data as well, right? So now, pre-processing in the live scenario will run in the microcontroller. So you have all these constraints again. So if you say, for example, in traditional ML pipeline, I was assuming data is not synchronized. Data has significant knowledge and I'm fine. My model is strong enough to account for this noise and all these fancy things in ML. Well, you might be able to account for it, but with a cost of compute that you cannot really bear to pay in a normal MCU. So in that case, you have to minimize your, I mean, the short summary is if you can really minimize your pre-processing stage compute requirements, then that's better, right? Was this considered to be better in classical ML? The answer is no. The answer was fact, you can really make your ML pre-processing stage as big as required. It even makes you better because you'll be resilient to more noise, right? But that's not the case for a microcontroller, right? And one thing we have observed is that most of the tiny machine learning works, in fact, ignore that stage, ignore the live data streaming stage. They start from the fact that I have a model and maybe you assume that the data is pre-recorded or something. So you ignore the sense of data collection, which is in a practical system, that's not true. In a practical system, the data is live. It's coming from, again, a camera feed on a drone. It's coming from a patient live signal. So you have to account for this pre-processing stage in your project, for example, right, that you're going to do. And also in any normal TinyML pipeline. Good. So summary is you want to minimize its compute, right? Because it's part of your end-to-end latency. So it's going to impact latency. It's going to take memory. It's also going to require a lot of math operations that will exhaust the CPU frequency. Good. That's the pre-processing stage. Then we go into the feature extraction. I think I did already mention some of this before we read the paper. Is there anything else you want to add in the feature extraction?
Yeah, you will only look at peaks, maximum points because these are cheap, not require much application. But for example, looking at the frequency domain or the transformation, this take a lot of computation time.
An excellent point. So in this particular case, again, reading stuff from Vital data, if you look into the classical machining pipeline, for example, to infer blood pressure from ECG, PPG, what we have done is they extracted 40 plus features, including some stuff that would require transferring stuff from the time domain to frequency domain, doing what they call inflection point, have a square root and division. Those things are okay, again, if I have a cloud compute. Now you need to start saying, well, if I need a floating point division, please avoid that feature, right? Or do some approximation, right? So this is where the hardware challenge we discussed last time come into play. You know what you have in your hardware. Do you have a floating point unit or you don't? What is the width of the data that you get? How many cycles your division will take in a microcontroller? All of these things are low level that normal machine learning pipeline never thought of, right? And they really impact your runtime, right? If you want to finish within, again, 10 milliseconds, well, again, I don't even one second, and with a certain power budget, with a certain compute, certain memory, these low level decisions you have to take into account, right? That's for the feature extraction. So the summary again is minimize your features as much as you can. This is going to impact accuracy, but you have to pick up the features that are important to you, and you can do in your compute units as fast as you can. Good. Feature extraction. What is after? After we extract features, what do we do?
Model training stuff.
Yeah, you need to train your model, right? And when you train your model, the first decision you make is what model you adopt, right? From the classical machine learning, for example, are we doing linear regression? Are we doing polynomial regression? Are we doing SVM? Are we doing adaptive? What are we doing? Are we going for CNNs, right? What type of CNN? So choosing the model also is going to impact your compute, right? Now, this is a decision that you make deliberately, right? Maybe after some testing, after some stuff, right? And I told you at lecture 1 that there is a trend that neural networks and deep learning is in fact the winning approach in all this discussion. But that's not true, especially for tiny machine learning. Some problems are better solved with classical machine learning, right? So it's very important to consider also how much compute you need, especially for tiny machine learning, yeah?
And the pre-processing that you said, because you don't technically you would not want to compute. You do pre-processing, you pick a model that wouldn't need pre-processing.
An excellent point. Yeah, so there is an interdependency between these stages. One of your breaking points of the model is they don't require a lot of pre-processing. That's to extract features. That's one thing. And also you don't want to make a model that would require heavy compute. So as the simpler, the better, if it gives you the required accuracy, right? Yeah.
And when the microcontroller is during inference phase, is it a sequence process like the data extract, then you run inference and you have output? But if let's say if this process takes longer, then I might have the second signal coming in.
Yeah.
While inferencing is running.
Yeah.
Well, I'm curious, like when we design the expressions, do we need to consider all this length?
Yeah, an excellent point. So your question is more about the real time. A constraint that you have in tiny machine learning is that, especially when you deal with real data, it comes live. And it is the one defining your end-to-end latency. Remember last time we talked about predictability and deadlines, and we had the example of airbag, right? Where you have to meet your task deadline. So this is coming from this definition. Is when do I need to repeat that task? Usually it's at the rate of the incoming data, right? If you're talking about a patient, for example, how fast or how frequent you read the ECG, BBG data from the patient, because you need to process that data and enter it to the inference field, right? And your inference must finish before you get a new data. Because once you start adding a data, if you're, from a queuing theory perspective, if your outgress is slower than your ingress, right? Like if your output is slower than your input, what's going to happen? They're going to accumulate a lot of data in the memory. And then you run out of memory because you have very limited memory. So you want to make sure you process as fast as the data is coming. And this is the real-time requirement that you add in the tiny machine learning.
So the optimization might not just happen inside the model, but also outside the model, which is the abstraction part. And it may be the inference part or maybe a safety part.
Yes, 100%. Yeah, this is what is this telling us, right? Is that you cannot really focus only on the training as we used to do in the tiny machine learning. You have to consider the end-to-end pipeline, right? And in reality, if you hear even like the NVIDIA CEO talk, like in CES 3 weeks ago, right? They were talking when they were talking physical AI for robotics. He said for the first time, we really care about the end-to-end pipeline. You want to get the data and do all the processing and take the action end-to-end in real time, right? This is again in classical machine learning, that's not the case, right? So you have to take this into account. So the challenge that we discussed last time, right? So in picking up the model, is there anything else that we need to consider? What about the memory size, right? Yeah. There was that figure in the paper here that was discussing, for example, for classical machine learning, right? We are comparing the inference latency, which is related to the discussion I was having with your friend here about you need to finish within like a reasonable time that is defined by your application, but also your accuracy, which is mean square error, right? That is required also by the application. It's domain specific, but how much memory I take, right? How much memory I take is very crucial, right? Because again, we have very limited memory. So if you have a very big model that requires a lot of memory, then well, it might not really be ideal for your case, right? So you compare, for example, linear regression. Linear regression is your simplest. It's a linear equation, right? So how many parameters do you have in a linear regression model? two, right? Because what do we really mean by linear regression for those that are not aware of machine learning? You know the equation y equal ax plus b. It's a linear equation, right? You only have two parameters there, which is the gain, the sensitivity, which is ax, right? So if we write this down, we have a pen here.
Professor,
Yeah.
can you expand X as a vector so you have multiple features as well?
Yeah. That's true. So we're talking about, yeah. I mean, we're talking now about the number, not the size, right?
Mm.
So this is a linear equation, right? This is the simplest machine learning model you can have, which is usually when you did a fitting, linear fitting in Excel, this is really what it does, right? So this is your sensitivity, which is how fast y is changing with X, and this is your offset, right? These are your two parameters in linear regression. So that's the simplest thing you can store. Now your point is that these are not necessarily scalars. They can be vectors, they are completely true, right? But their number is still two, right?
Yeah.
Their size can be different, that's correct, right? But if you compare this, for example, to SVM or something else, right? Like a tree-based machine learning model will have a lot of parameters that you need to store, right? So the memory is going to really vary based on what model you pick, right? Now, you know that, for example, in this microcontroller, I have something like 4 kilobytes of memory, something very limited, right? And then I know that this model is going to require 10 parameters. Every parameter is the size of 16 bytes. You do the math and you see, do you fit, you don't fit? So you see there is a low level analysis here that you need to make. Good. So the model size in terms of memory is going to impact your decision as well. Good. This is not only for classical machine learning when you just pick a model, but also for the size of your neural network, right? In reality, we can come up with an analysis exercise to say, pick up your microcontroller, for example, the Arduino Belli Sense, know how much memory you have. And then you can know mathematically, analytical way, the maximum number of weights you can store in your memory, right? Because, for example, you say I'm going to represent my weights as 8-bit. Let's say I do quantization. So every weight parameter is 1 byte, correct? I know, for example, I have 4 kilobyte memory. So I can bear 4 kilo number of parameters, 4096, like weights, right? So you can do that math, right? And this math is being done by people at the moment to ensure that I can fit or I cannot fit. This is under the umbrella of, can you provide an analytical model, which is an interesting research project, by the way, if someone is interested in doing TinyML research that is innovative, not just redoing an application wise. So you can build an analytical model to say, give me your neural network, give me the requirements of that or the specification of the microcontroller you are considering. I'm going to tell you without you running it at all, whether you fit or you don't fit, right? How do I do this? Well, you do the model like math that we have done in the memory, but you can also do the compute, right? So building an analytical model can simplify a lot of things, right? Because you can make the decision choice. One of the challenges people are facing at the moment is, what network do I pick? And what microcontroller do I pick? And the state space is huge. In the embedded domain, we have tens of microcontrollers. In the machine learning model, well, this can be an infinite. Like even you pick up like a neural network, you can reduce its size, make it big, small. So it can be an infinite state space. So how I do really reduce that state space through a framework that does the exhaustive search for me, but analytically, right?
I have like a microcontroller, say 256 kilobyte RAM. I have a model with say 100 kilobytes. It's not enough for me to look at the size and say, because I'm within the size, then nothing.
Yeah, it's not, yeah, that's an excellent point. It's not the only constraint. So this can be an exclusion. Well, it's necessary, but not sufficient, right? So if you exceed, then you don't fit. If you are within, well, there are other problems that you start considering. You see what I mean? Like if what you're saying is that if I'm 100 kilobyte and this is 256, so I can't fit. Does it really mean I'm going to run? Well, not necessarily, because maybe my compute requirements are bigger than what the microcontroller can do, such that the latency will be huge. Or maybe my code size, because your memory is also not one memory type, right? I told you earlier, I think that we had part of this project is that some networks didn't fit in some microcontrollers, not because of the data, not because of the weight sizes, it's because of the code size of the network. The network was very complex to the level that the instructions themselves didn't fit in the code size, right? So there are other considerations you have to take into account. But I'm just simplifying the problem is that you can build an analytical model. It's an interesting problem that, as far as I know, no one really did so far, right? You can build some analytical model that takes this as an input and gives you an early decision, right? At least an estimate. Good. That's with regard to the model size. Then we move forward, we picked up a model, then what do we do? Yeah. Data scaling. Okay. Yeah, there is a discussion about data scaling. First of all, what is data scaling for those that know machine learning?
Standardizing.
Yeah, standardizing the data. Usually, you might be getting the data at different scales, right?
Different.
Yeah, maybe there's a noise into it, and you want basically to scale your data, make it to the same scale, such that simply the training is unified, right? Now, this scaling is a standard way in the training of traditional machine learning. Again, why it's problematic for us? Why are we revisiting it?
Extra steps.
It will take time and requires compute, right? Scaling is division multiplication, right? So that's very, very problematic because if I want to do division, it's very large latency, and maybe even some microcontrollers don't have a divider, right? Don't, like their pipeline is not really doing division. They just do division iteratively by subtraction. So it takes tens of cycles, right? So what do I do? Something, for example, if I remember what I've done in this paper is we avoided, or maybe not written in the paper because we tried and we choose something else. But you can also do the scaling by doing the division through truncation or shifting. Like you replace the division with something similar, right? What are you losing if you do this? Precision, right? Accuracy. So you impact the accuracy. So every decision you make to make things better, it will really blow off on the accuracy side. And then you have to make that trade, right? So again, I'm going deeper, low level right now as an exercise for you to say, well, what we discussed in these two lectures is not something really, well, theoretical and just sit down and listen to it. It's something that you have to do practically in a TinyML project, right? I'm expecting you when you do the project, you think about these things. Okay, so the data scaling. Then what is after? So I scaled the data. Yeah, now you finish your training and you end up with a model, right? In a classical machine learning, you are done, right? Because you can run that model and you're doing the inference. But in TinyML, we already discussed this at the beginning of the lecture. What do I need to do? A Python model, a very beefy model doesn't fit into my MCU. I need to convert it, right? So the conversion can be done using many flows, right? TensorFlow Lite is our standard flow in that course. I think in this paper, we have used something else that is open source. But it doesn't really matter, right? So I end up with a quantized, pruned C model that fits into my MCU. Good. So this is the model conversion. Now, I converted the model. Then I need to really, well, evaluate it into my my MCU. Then I think something we discussed also in this paper is right now it really becomes a feedback loop, right? Because maybe you try it here, right? Maybe you try it in your target, but you discover that's not very well optimized for the target. What do you do again? You go back and you try to really tune, right? Or even change the training. So you add extra more to the training, such that simply you tune the model more to really optimize it for the target device, right? This feedback loop, again, did not exist in traditional machine learning. Why? Because this target model, which is your embedded microcontroller, adds extra constraints to you. Good. And then you just deploy and do the real-time inputs. Good. Anything to add from what you read? What about the time requirement, the end-to-end latency requirement? Oh yeah, that's for the evaluation. But what I mean is that in terms of consideration for TinyML.
Latency has to be.
The latency has to be, yeah, but minimal, that's as in terms of optimization, right? But generally in especially embedded critical systems, in healthcare domain or automotive or a drone, you have a strict timeline. It tells you, for example, I need to finish perception and object detection of YOLO in my embedded device on the drone within 20 milliseconds, right? Otherwise, with my speed of the drone, I might hit into the object, right? So there is a defined deadline from the use case. And this defined deadline means I must finish my end-to-end from getting the live data from the sensors all the way down to finishing the inference and taking the decision. And taking the decision means, well, I just change my motor angle or do something in the robot or for the healthcare device, like the one in the estimation, you have already done your estimation of the blood pressure and you write it somewhere, right? You finish this all end-to-end latency within that deadline, right? So you start from the domain, gives you a deadline to ensure correctness, right? Last time we defined the embedded system as its correctness does not depend only on functionality, but also on the timing of the functionality, right? So you come up with a deadline, and then this deadline, you have to finish your inference within this. Now, what if I didn't finish my inference within this? What do I do in TinyML? Yeah, you go back to this feedback loop and do the tuning part, right? Maybe you end up with changing the model completely because you are really not meeting the timing requirement. It's not about efficiency, right? In ML, it's more about throughput. The faster, the better, but there is no hard requirement, right? In real-time system perspective or in the embedded domain, we used to call this a soft real-time. I mean, it's convenient to be fast, but there is no hard requirement there, right? In TinyML, that's not the case. In many applications of TinyML, it is a hard real-time system, which means if I don't meet my timing, I have to change everything else. It's not really an option. Good?
Yeah. So can we say that, for example, speed of inference versus accuracy, is that like,
It is a trade-off,
is
for
it
sure.
trade-off? Okay.
Of course.
Can I, for example, lower the accuracy just so I can meet speed?
True, up to a limit, right? So up to a limit. Because if you lower your accuracy, but you need your accuracy to determine whether this is a walking pedestrian or not, then it's still risky, right? So it's like you are trading functionality to timing. Both are important, right? And you can trade both for a limit, right? For in some cases, for example, I'll give you a practical example. For the drones and automotive and that stuff, there is a mode mandated by certification standards. This is called fail-safe mode, right? What do you mean by fail-safe? It means that if for any reason you determine that there is something that you cannot really control and you might go out of that control, there is a pre-programmed fail-safe mode that you reside to. This fail-safe mode does not have a lot of compute requirements because it must execute under worst-case scenario. In that case, you don't have any real-time requirements, right? It's more about I just need to maybe, for example, for a railway system, I need to stop the train. For a drone, I need to land safely for a known place. For a car, I need to park on the side of the street, right? So you define that system before, you define that mode, and it has its own timing requirements, right? Yeah.
How do we choose this deadline for a specific application? Is it through trial and error?
Yeah, it comes from, again, the domain itself. Like in many of the safety critical domains, it comes from a third party, not from you. It comes from the practical use case. In a project that you are doing, you do it intuitively. You say, for example, I'm doing this project and it's a voice recognition project. Then depending on what is your response time requirement, like if you say, for example, okay, Google, then Google does not respond within
10 seconds.
10 seconds, then you might get frustrated, right? But again, that's an example of a convenience, right? Soft real-time requirement. But if you say, for example, but maybe voice recognition is not the best example. Again, image recognition is an example about obstacle avoidance in a car, right? This is not about 10 seconds or 5 seconds. It has to be within what is your maximum speed, what is the pedestrian speed, whether I can stop or not, right? Or obstacle avoidance in a drone or a robot or that stuff, right? So it always comes from the application. Again, in our local project, you just do your due diligence. In the report, you have to justify why did you choose that you can tell latency, right? And whether this is meaningful for your application. Questions? Good. Okay. So yeah, as we said,